right, Advanced Math 8, we've got lesson 4.1.3, upper and lower bounds. So in this one, I've already kind of gone ahead and I've done the graph, so you'll probably want to pause and just catch up on my graph in a second there. But anyways, the situation in this one is not serial again, so I don't have to spell that, so that's good stuff. Now we're going to look at, in 1997, there's an anthropologist, they're out there, and they discover an early humanoid in Europe. The problem is the only complete bone that they find is the ulna bone, so the forearm. And the bone measures 26.4 centimeters in length. So here's the problem that they got here. They want to know how tall this person is. So they get the bright idea, you know what? We're just going to go around and measure a whole bunch of people's ulna bones. So that's like their arm, right here. So they're going to measure their arm, and then they're going to look at their height, and they're going to go, oh, we should be able to get an equation by comparing a whole bunch of people's arm bones and then their height, and then we'll find out how tall this person is. And actually, it's not a horrible idea because the ulna bone is actually one of the oldest units of measurement. A lot of ancient societies, they used to just like to measure. They would just put their arm down, and then they'd measure, and they'd put it down and go, okay, there's one, and then they'd go down, there's two, there's three. So they'd just measure a whole bunch of measurements with their arm. They called it a cubit. So I don't know if you've heard that before, but a cubit is just the measurement from somebody's elbow to their wrist. And so it's not a bad measurement tool. It's not very effective as far as being accurate, but, if you don't have a ruler or something, I guess that works. Anyways, today we're going to go ahead and use the data provided by the book because it just wastes a lot of time us coming up with our own equation. We've done it several times already. I'm going to assume that you can do it by now. So we're just going to describe the association. Then I'm going to tell you what the line of best fit is. Instead of us spending tons of time deriving that line, you guys know how to do it by now. At least I think you do. So I'm going to just assume you know how to do it. Good to go. Let's move on. So we're going to describe the association. Now this association, it's a little bit spread out there, like if you really look at it, right? But it does look like it's probably linear, whereas whereas the other one that we looked like had kind of like a curve to it. So we're going to go ahead and say that this is, I'd probably say it's a moderate. It might be weak, but I'll say it's moderate. I'll say it's a moderate linear, pretty much. It's kind of going in the same direction. Linear, moderate, linear, what's it called? Positive, because it's increasing from left to right. Association. And it doesn't look like there's really any outliers. So that's how I'm going to describe it. If you said weak, I wouldn't take points off for it because it's kind of weak. It's not super weak, but it's a little bit weak. So anyways, we want a line of best fit. So let me calculate it up in a second. I'm going to pause it real fast. I'll calculate it up and then tell you what I got for my line of fit. All right, so here's what I've got. I got H equals 3.9F plus 63.3. So 3.9F, that's our slope. F is the forearm length. H is the height. And in order to get my best line of fit on here, what I did is I said, okay, if I plug 20 in there, what would I get? And I ended up with about 141, so I put that point there. And I said, okay, what about 22? And I got almost, it was like 149 or something like that. And I said, okay, what about 25? And I plugged it in. It was like 160.8 or something like that. So then I'm like, okay, there's my line. So there's my line of best fit right there. And it actually looks like a pretty darn good line. It goes through the middle of the data. All the points are kind of spread out on both sides of it. So yeah, I'm going to say that's a fairly good line. Okay, what we want to do is identify the point that is the very farthest away from the line. Okay, so look at all those points and find the one point that's the farthest away from the line that we have there. So looking, that point's too close, that point's pretty close, these 2 points pretty close. One, two, three. I don't think you get any farther than this one. That's the farthest point. Okay, so this is my farthest point from the line. Looking over here, that's the point 24, what was it, 24,175. That's the farthest point away from the line, and we're going to calculate the residual for that. So remember, the residual is the actual minus the predicted and then that equals the residual. So our actual for that point was 175. Our predicted, we're going to have to calculate that. So we're going to do H equals 3.9. Forearm length is 24. And then plus 63.3. So I'm going to do 3.9 times 24 equals then plus 63.3. Comes out to 159.6. Let's just call it 157 and be happy with it. So I'm going to say that's 157. So this is minus 157. Okay, now looking at this, we would expect a positive residual, right? Because it's more than the best line of fit. It's higher than the best line of fit. And this is what we're getting down here. 175 minus 157 comes out to 18. We get a residual of 18. Okay, now what we're going to do is we're going to create, so we know that this residual right here is a residual of plus 18. So what we're going to do is we're going to create another point that is 18 below that one. Okay, so 18 below that one. So if I take 157 minus 18, that'd be 139. So where'd 139 would be like right about here. So this would be minus 18. So this one is 18 above the line. This is 18 below the line. And so what we want to do is we want to create dotted lines for the upper and lower bounds. Now, upper and lower bounds. So let's do the lower one right here. And we want this line to be parallel to this line up here. So there's my lower bounds. And then I'm going to do a upper bound above that one. Let's do green because it's pretty. And this would be my upper bound. Now, what are we doing? Why are we doing this? Does this make any sense? So what we're doing is we're saying, okay, our data all fell within positive or negative 18, right? Because our biggest residual was right here. So what we're saying is our data is falling in between positive and negative 18. There is no data points that are beyond those bounds. I've got an upper bound. That's the highest point of my data. And then I just used negative 18 for my lower bound for my data. So everything's falling inside of that. I'm going to tell you why in a second, why we're using those. So I want to write the equation. So the upper bound equation, now remember, these are parallel lines. So the upper bound equation should have the same slope, 3.9f. And since this one has a y-intercept of 63.3, this one should have a y-intercept of 18 more than that. So I'm going to take the y-intercept of 63.3 and add 18 to it. And that would be 81.3. And that'd be my upper bound. Now my lower bound is 18 units below this line, but it's parallel to it. So it's still going to have a slope of 3.9 because parallel lines have the same slope. But this time I'm going to take the y-intercept and I'm going to subtract 18 from it. So 63.3 minus 18. And I end up with 45.3. All right, now we're going to get to this part and actually use our upper and lower bound. So using the upper and lower bounds, create a range of values for the forearm length. So here's what we're saying here, is that the forearm that we found, that ulna bone that we found, was 26.4 centimeters. Now we can predict what the actual height is going to be. But look at our actual height. So, I mean, we can predict what our height is going to be using this line. But look at all of our actuals. Our actuals were hardly ever on that line. Well, they were never on that line. So what we're saying here is that this ulna bone should probably be somewhere in this range, right? So we saw when we tested people's arm bones with their heights, everything fell within this range using this upper and lower bound, using the biggest residual. So what we're going to do is, okay, what's the tallest this person could probably be? That's the upper bound. And what's the shortest this person could possibly be? So we're going to plug in 26.4 into the forearm lengths there and see what we get. So the upper bound height would be 3.9. The forearm was 26.4 plus 81.3. So 3.9 times 26.4 equals plus 81.3. Comes out to a height of 184 centimeters. Okay, that's the tallest we might think that this person, this ancient human, was. Let's see how short we might have think he is. So 3.9, and we know that the ulna bone was 26.4, so I'm going to plug that in for the forearm length. And then my lower bound y-intercept was 45.3. So we get I know this is boring, just listening to me type stuff in. I should have probably paused, but I didn't. So we're just going to listen to me typing stuff into a calculator. So 3.9 times 26.4 equals, and then I'm going to add 45.3 to it, and I get 148. So here's what I get. Well, the person can be 184 centimeters tall, or he can be 148 centimeters tall. That's a pretty darn big, wide range. So was our model useful? Probably not, because this guy could have been really tall or really short. We have no idea. There was not a good enough association between our points to tell us, and really it's because of this word moderate. Our points were so spread out that using them to actually predict something isn't very helpful. So what we want when we have associations is them to be strong associations. Strong association means that our prediction is going to be more useful. A moderate association means our prediction is less useful, like this one. 184 and 148. That's a lot of centimeters difference between them. Just to give you an idea, let's see, 184 minus 148. That's 36 centimeters. Now this is 15 centimeters. That's a lot. So 15 plus another 15 plus some more. That's how different in height. And that's ridiculous. That's like over a foot difference. So no, this model is not helping us because our data is a moderate association. So if the data would have been more strong association, then the upper and lower bound would have probably given us a better range of heights to pick from. So the model was not useful. Not useful because the range of heights was too great. All right, and here's where statistics kind of is misused in real life. A lot of times you'll get people say, I found this, and therefore I'm using my model, and my model says this. But yeah, how strong is your association though? You might say your model predicts that, but it could be way above it and it could be way below it. So people misuse statistics a lot, and then people don't know math, and so they just believe them. So looking at people's math, which is what people usually do in something called peer review, when they look through their data and look through that and said, yeah, that we agree with this, or no, we don't agree because we're looking at your math and we're looking at how you decided, how you came up with your conclusions, and they double check your work for that. So the models are not always going to be helpful, but our upper and lower bounds are one way we can see how helpful a model can be by giving us a biggest number and smallest number to look at. That's all I got for you. Math hard. Don't trust anybody. All right. See you later. Bye. Okay. You should probably trust your parents and stuff like that, but question authority. All right. See you. Bye.